Gekhtman, who will talk about Poisson's side of the theory of cluster algebras, cluster varieties.
Спасибо, Diem. Thank you. Thank you for the invitation. This is my first time in Yaroslavl, and I hear it's beautiful, but right. We now travel every day. It becomes easier because it's virtual. So I want to start by apologizing to those who have heard this before, because this is going to be largely an overview of mostly our work with Mr. Shapiro and A Vainshtein on connections between cluster theory and Poisson geometry, in particular Poisson structures on Lie groups and Poisson-homogeneous spaces. So I'm going to start by sharing the screen, and then I will try to use it mostly as a blackboard, but if I will need some, more involved formulas or pictures, I will switch to slides. And I'm going to start with very basic overview. So it is well known that say in theory of integrable systems in particular, it's important to have nice coordinates. So you can view this as all this business with cluster transformation as a convenient tool to produce large family of convenient coordinate systems. So what we're going to be concerned with most generally is some Poisson varieties. They all will be algebraic, and in our particular case, they will be in addition equipped with an action, with an action of a torus. I'm going to deal mostly with a complex situation, so we will talk about holomorphic Poisson structures, but this is a general setup. So we're looking for nice coordinates in this situation, and we're looking for transformations between these nice coordinate charts. But let me just start with simplest examples that we all know of Poisson structure. So we know that the simplest example of a Poisson structure, of course, is a canonical Poisson bracket on R to N, when we have coordinates P and Q, and Pi, Qj is delta Ij, and the rest are zero. So the constant Poisson structure, and well, in many problems, it is convenient to find coordinates which have this shape, and this are called Darboux coordinates, right? So this one is constant, right? And the next, probably in complexity, is a linear Poisson structure, and these are connected with Lie algebra. So Lie algebra has something that satisfies Jacobi identity, and so you can use that to produce a Poisson structure on the dual of the Lie algebra. So you take two linear functionals associated with elements of Lie algebra. So psi and eta are in Lie algebra, and L psi as an element on, let's say, another, I don't know, zeta is given by, let's suppose we have a pairing right of zeta and psi, and so this is a linear structure. Okay, so this is what's called Lie Poisson. And then the next case would be quadratic, and so we have some So in some coordinates, xi, and so the bracket of xi, xj is a sum of with some structure constant of Cij alpha beta x alpha x beta, and this is already quite complicated, and there is no complete classification. In this case, one can, well, distinguish the simplest possible situation, and that is diagonal quadratic, which is of the form xi xj Poisson bracket is equal to just Cij xi xj, no summation. All right. So this is the simplest possible quadratic Poisson bracket, and this is the bracket for which we use the term, which may be an unfortunate term, but it is now widely used, log canonical, right? So all that it meant, all that we meant by it is that if you take logs of this coordinate, then you'll get a constant bracket. All right, so already here there is an interesting, not very complicated, but interesting observation by Owenhouse and Machasek that in some sense this diagonal quadratic log canonical bracket is the simplest possible quadratic Poisson bracket. So what I mean by that is that there exists no rational transformations, coordinate transformation such that this log canonical Poisson bracket reduces to a linear or constant one. So what it means that if you start with some naturally defined quadratic Poisson bracket, this log canonical thing is the simplest one that you can hope for. All right. So okay, but on the other hand, there are plenty of not so simple quadratic Poisson brackets, and the one of most interest to us is the case of Poisson-Lie groups. So let me just briefly remind what it is. Again, I apologize if it's all well familiar, but I was told not to assume anything. So in this case, G is a Lie group equipped with a Poisson bracket, and we assume that multiplication map, where you take two elements and send them into their product, is Poisson. So that's the definition of Poisson-Lie group. So they first were defined by Greenfield as quasi-classical limit of in the study of quantum groups, and there is a beautiful theory due to Greenfield, Semenov-Tenchansky, many other people, and this is closely related to theory of classical R matrices. But I will concentrate today first at, well, on some standard, rather simple examples. And so the simplest example is the following. So suppose our G is, let me call it B2 plus, just a set of 2 by 2 invertible triangular matrices, and the Poisson bracket is just a product of those two coordinates, right? And similarly, you can Another example is B2 minus A inverse B0, the same bracket. Okay, so this is an easy exercise to show that this is a Poisson-Lie structure, right? And it has this property, this log canonical property. The Poisson bracket of two coordinates is equal to constant, in this case, constant equal 1 to the times their product. All right, this is the simplest Poisson-Lie group, but of course, there are much more complicated one, and so the next one in complexity, which is not like this at all, right, is, or at least not in standard coordinates, is what's called standard, it's called Skleanin Poisson bracket on, well, let me use for now G equal to GLN, and there are several descriptions of it, so you can write it in formulas. So suppose you have just a matrix X, Xi, J, and then you write Poisson bracket of Xij, Xi prime, J prime is 1/2 sine I minus I prime plus sine J minus J prime times, and here let me emphasize it in different color, times X I J prime X I prime J. So it's not log canonical because there is a mixing of coordinates. So this is one way to describe this Poisson bracket, and there is another one, okay, so I don't want to talk about our matrix description at this point, but another one is that if you take this B2 plus or minus and then send them, let's call it rho I, as a, well, canonically embed these groups as diagonal blocks located in rows and columns I plus 1, and the rest will be ones and zeros. So all these maps are Poisson. All right, so that's another way to describe it. And here we have an interesting situation already, because in natural coordinates, this bracket is not log canonical, but we know that bracket in this B2 pluses, B2 minuses is log canonical. And we also can observe that a generic element of GLN can be obtained as a product of factors of the form rho I B2 plus minus. All right. So I will illustrate it with a picture, but this hints at the possibility to find different coordinates on GLN that will have this nice property of being log canonical, and maybe to do it not in a unique way. So here I am actually just briefly referring to Vainshtein, the Levinsky factorization. All right, so let's just illustrate the situation by first replacing the simple matrices that live in B2 plus minus with pictures. All right, so as you recall, so if you have an element in, so let me write down element in B2 plus, and I'm going to replace this element with a picture of the following shape. So I will write it down and then explain. So there will be some arrows, and then I will write here A inverse B, and I'll just say it in words what I mean by this picture. So I am representing this 2 by 2 matrix with a diagram which has well, 2 sources and 2 sinks, and I can move along this diagram from left to right only, and to compute an entry of a matrix, I consider all possible paths from, well, say, from a source I to sink J on the other side, and then I will compute product of weights along the path, and then I will add all such products, and that will give me a matrix entry. In this particular case, there is nothing interesting going on because there is only one path from 1 to 2. There is no path from 2 to 1, and one path from 2 to 2, and one path from 1 to 1. All right? So we replace it with a picture like this. Okay? And similarly, if I have, let me use different letters, alpha, alpha, inverse, beta, I can replace it with another picture, which looks like this. Same arrangement, so weights. Well, so I have here alpha, alpha inverse, beta, okay? And then what I can do, I can multiply, of course, matrices. And it is easy to see that with this setup, when I multiply matrices, I can multiply these pictures as well. And that just results in concatenation of diagrams. So I can say that, well, the product of these 2 matrices produces for me an element in SLN. So let me write it like this: x11, x12, x21, x22, right? And here it's slightly more interesting, right? Because I can actually compute this product using my pictures as well. And that will give me, so in this case, I'll get, why did I, sorry. This should have been the other way around. So I'll get, what will I get? 2 to 2 will give me A inverse, alpha inverse. And then 1 to 2, there is only one way to get there. So I'll get B and then alpha inverse, so B over alpha. And then the other way around, I'll get beta over A. And the only more complicated term will be in 1-1 position, because now I have 2 paths that can go there, right? So I have path that goes like this, and another one that goes like this. And that will produce for me the following expression. It will be A alpha plus B beta, all right? Okay, so, right, so this is how I compute my matrix entries using diagrams. And then I can observe that as far as Poisson brackets go, so I knew that the map is a Poisson map, this embeddings of upper triangular and lower triangular maps. This is a Poisson map. And I therefore know that if I had a log canonical bracket between A and B and alpha and beta, then any monomials of them will also give me a log canonical bracket, right? This is just the properties, this is just by Leibniz rule. And so immediately I can see that the bracket between x22 and x, let me even, I'm not going to write them actually. I'm going to just list them. Sorry. Okay. So this immediately tells me that the coordinates x22 and say x12, right? They're monomials in original coordinates, so everything will be fine. And in fact, yeah, x12, x22, x12, and x21 will be log canonical. All right. Just because of this picture. But then if we use an opposite factorization, okay, then it is also easy to see that x11, x12, and x21 are log canonical. So even though the original Poisson-Lie bracket, the standard Poisson-Lie bracket that we considered before is not log canonical, right? So we found coordinates which are two actual systems of coordinates which are log canonical. And so these two systems are related by a very simple transformation. We'll know what it is, right? So we'll just compute the determinant. So x11 is, since we're in SLN, it's simply 1 plus x12, x21 divided by x22. So this is a transformation. Or more generally, if we're in GLN, then this transformation looks like x11 is equal to 1 over x22, and here I'll have a determinant plus x12, x21. Right, so we started with some Poisson bracket, which is not log canonical. We found two coordinate systems which are log canonical, and they're related by this transformation, and that is a typical example of a cluster transformation.
But here, the right-hand side belongs to one factorization and left-hand side to another factorization. Is it correct?
Well, but you see, I can my matrix entries do not.
You have two factorization. You have two factorization, right?
Yeah, right, exactly. I have two factorizations. So factorization tells me which coordinates will be log canonical, but matrix entries do not know how I decided to factorize them, right? So in the end product, you just get a nice coordinate system that does not, well, that was discovered using factorization, but it does not know that, well, which factorization necessarily I used to begin with. All right. So this can be extended. Yeah.
Can I ask something?
Yeah, sure.
The group is GL2 or SL2 or what?
Yeah, so I can make it into GL2 by adding. Determinant in this Poisson-Lie picture, determinant is always a Casimir, so I can add another weight, right? So let's yes, I'll put another weight here, say D, right? And then that makes it into GL2. So I started with SL2, but it is easy to adjust to make it GL2.
I have a very naive question. You say that you have a system of coordinates, but you consider 3 coordinates for the 4-dimensional manifold GL2.
yeah. So again, so if I extend from SL2 to GL2, then there is fourth coordinate, and that will be the determinant, which is
okay.
yeah, which is a Casimir. And this is a very good question, in fact, because there are these coordinates which are special, and I will talk about them in a second, which I cannot change. So I cannot replace. Notice that I just replaced one coordinate in this two coordinate chart. And I cannot replace x1 to x1 or the determinants. They'll stay fixed in all such coordinate systems, and those in cluster Linga they're called frozen variables. Okay, so maybe let me draw another example now that we can replace matrices with pictures, just as an illustration that this works in more general situations. So another example, so let's now go with GL3, okay, and I will just draw a similar picture. So this will be a picture describing a generic 3 by 3 matrix, 1, 2, 3, 1, 2, 3, again following work of Vainshtein, Fomin, and Levinsky. And so let me use this factorization now. Okay, 1, 2, 3, and 1, 2, 3. And so how should we view it? So I can view each little piece. So let me separate them. Right. So we know that multiplication is concatenation, right? So and I'm not going to draw weights right now, but as we discussed before, so embeddings of this B pluses and B minuses, diagonal embeddings are Poisson maps. So how should I view this first segment, right? This first blue segment on the left. If you look at it carefully using our rules, what it is a 2 by 2 triangular block that sits in the first rows and 2 rows and columns, and embedded into 3 by 3 matrix. And the second factor, or the second slice in this picture, embeds again 2 by 2 lower triangular block in rows and columns 2 and 3, and so on. All right. And so now if I add all the weights, so again, I don't, well, I'll just show a couple of them, like here, A inverse B, and then in the middle, just so the number of weights will be more than we need, but that's okay. In the middle, I will put this Casimir, if you wish, so which is diagonal, let's say D over here, and so on. So there will be then exactly the same. So there will be more weights than we need, but you can operate with weights and put all the horizontal weights in the middle. So I don't want to talk about this much, but what I want to emphasize that we can find exactly 9 minors. So this is our element X in GL3, exactly 9 minors of X, which are monomial in weights. And if they're monomial in weights, that means that they will form, as I explained before, a log canonical coordinate system. All right. But if I change the order of factorization, which I can do, right? So we can factor in different orders. So different orders of factorization will lead to different collections of monomials, of minors, therefore we'll have several log canonical charts. And all of them, all connected by sequences of transformations of the form, let me put it this way, old variable times new variable equals sum of two monomials in one chart. And this is how general cluster transformation looks like. Okay. So in fact, these transformations will be modeled on classical determinantal identities. So cluster transformations, well, it turns out we all learned them in undergraduate linear algebra classes, if we were lucky enough to cover this. So identities like, if you wish, Dinano, Jacobi, Short-Kluger, etc. All right, so maybe I should show a portrait of such situation, but I will do it in a second. But are there any questions?
Yes, Misha, I'd like to make precise principal point. So you ask that the Poisson bracket on the group be log canonical.
Well, Poisson bracket on the group is not necessarily is not log canonical in natural coordinates. So let me go back to this formula, this one. Right? This is not log canonical at all, right? Because the bracket of two variables is product of some other two variables. In a more general situation, it can be even more complicated than that. Okay. But I found a birational change of variables in which this bracket is log canonical. So that's
and you do this by different choices of
right. So here there is a combinatorial way to do it. So combinatorial data is the order of factorization, and it is governed by reduced decompositions of the longest elements in the while group. But I don't want to go through the detail. But so here there is a combinatorial picture, and when I change the order of factorization, my coordinate system changes accordingly, and you can trace these changes by using cluster transformations.
Is this condition sufficient to extract this cluster structure? The condition that the parameters
right. So this is a very good question, and this is what I wanted to address next, right? So let me just formulate a question or problem or strategy in general, right? So what do we want? So maybe I will even switch for a second to slides. So can you see the slide? Yeah. So let's just review what do you want. So now suppose we have a Poisson variety in general. So it's an algebraic variety that admits a toric action. So I may not have time to discuss why we need it necessarily, but let's have it, right? And so what we want is to find a family of coordinate systems that we will call clusters that have these nice properties. First of all, we want them all to be homogeneous with respect to the toric action. So in our previous example, what is a toric action? So we have matrices, we can act by diagonal multiplication on the right and on the left. And of course, all the minors are going to be homogeneous with respect to this action. All right. And then we want every such coordinate system to have this properties that, that it is log canonical. So we'll call this coordinate system compatible with Poisson bracket. And I know, again, this is another bad term because this is not compatible in a sense of pencils of Poisson brackets. So it will be, in a moment, it will be compatible with a cluster structure. So again, the property, as I discussed, the bracket of any two coordinates is some constant. We can make it integer constant times the product of these coordinates. And then we want every two such coordinate system to be systems to be connected by transformations which are not only birational, they are actually Laurent polynomial in both directions. And if we're really greedy, we also want every regular function on our variety to be a Laurent polynomial in terms of every one of these coordinate systems. So we want a lot of things from this situation, right?
Why you can make everything integer?
No, well, okay, I slightly misspoke. I want the requirement that omegas are rational, and then that is a requirement. Rational, and then then I can scale
scale the bracket.
Yeah, exactly. Yeah, thank you. All right. So this is what we want. Okay, and okay, you want it, but how do you achieve it? And so again, I will stay with the slides for a few moments. So what do we see? So first of all, the first step, and there is no general algorithm of how to do it, is to find one coordinate system that satisfies these two properties of being log canonical and being homogeneous with respect to toric action. And in our previous example, we were lucky because we knew that we have the small Poisson-Lie subgroups that which are log canonical and embed nicely. And well, we know that all minors are homogeneous. But well, suppose we found it. All right, then we're getting into a cluster business right away. So I will explain how this step works. So then we will construct a quiver, so directed graph on n vertices where n the dimension of our variety. And what this graph is, so well, we had on previous slide, we have this matrix omega ij, which is made out of rational numbers, right? And you can consider an inverse or partial inverse of that matrix. And well, you scale it appropriately, so it's integer matrix, and you view this inverse as an adjacency matrix, so it will be Q-symmetric, generally speaking, well, almost Q-symmetric. So adjacency matrix of a quiver, right? So you have entries in this matrix, and each entry just tells me how many arrows are between vertex between two vertices in my graph. And so we place our functions xi at vertices of this quiver. So I will illustrate all of this by an example. So, but this is a general strategy, all right? And then we will construct Laurent polynomial maps, which are compositions of these cluster transformations, which I haven't defined, but we just talked about the general shape, right? It's product of old and new is sum of two monomials. And then, since I go from one coordinate chart to another, my Poisson bracket changes. It's still log canonical, but it changes, right? So this matrix omega will change, and so its inverse will change, and this will result in a change in our quiver. Okay, so this is maybe a lot to absorb, but let's go through the example, right? So the third property actually is guaranteed by Levinsky Laurent phenomenon, but I will refer to it in a second. So how do we do this, right? Well, then we also wanted to restore every regular function to show that it is generated by our coordinate system. And again, so part one, and the first step and the last step require just some ad hoc work. But in the middle, it's kind of algorithmic. All right. So what is this clustered transformation? So now, well, finally, I will get to some of the basic definitions in the cluster series. So we have two coordinate systems, and we'll call them adjacent if they're almost the same, if they differ just in a single variable, right? So I will take one variable away and replace it with a new one. So I took away xk and I replaced it with xk prime, and they are related by this identity. So the old one times the new one is equal sum of two monomials, and the first monomial is a product over all arrows that point to vertex number k in my quiver. And the second term is a product of all coordinates to which arrow points from this vertex k. So we'll see example of this soon. All right. So, but is there a question to this definition? Is it clear what's going on? So,
but will you explain how the quiver appears in this?
Right. Yeah. Yes. Yes. So I'll explain that when we'll get to an example. So all right. So okay. So what again before I explain that? So what happens to this quiver? So as I said, well, maybe I should actually switch back for a second. So relation between quiver. So we had a Poisson bracket xi xj equals omega ij xi xj. So this omega ij together, they form a matrix omega, right? Now, one thing that I should mention, so some variables were not allowed to touch. They are considered frozen, right? So so omega can be drawn like this. So there is part of it, let's call it omega 1, and then there are other parts. So the variables that correspond to this part, let's say there is m of them, they are frozen. I'm not allowed to touch them. Okay, just so that we know this for the future reference. And then there are n variables that I am allowed to touch. Okay, so what I'm going to do is find under non-degeneracy condition, it's always possible, find a matrix B, which is going to be n plus m by n, such that B times omega is equal to identity of size n and then 0. Okay, so this B will be, well, up to scaling, it will be integer with pluses or minuses in it. And so from this B, I will draw a quiver Q where we have n plus m vertices, and between any two of these vertices, the number of arrows is equal to Bij. So if Bij is negative, then arrows point in the opposite direction, right? So when I change coordinates, my omega changes, and therefore my B changes, because this relation stays the same, and therefore my quiver changes. And that's what quiver mutation is. In fact, our whole, well, the way we entered this with Misha and Alex this year, we were trying to understand the definition of matrix mutation by Fomin and Levinsky somehow geometrically, and then it turned out that it's not nothing else than a change of coordinates, as a change of Poisson bracket under the change of coordinates. All right. So what kind of transformations this gives us actually? So this is an example what happens, how the quiver mutation works. Here we have suppose we have 6 coordinates, right? And they attach to vertices of this initial quiver. And suppose I want to change coordinate number 2. So coordinate number 2 will become a product of x1 times x3 because those point to 2, plus x5 because this is only arrow from 2, divided by the original coordinate. So this is a cluster transformation. And what happens to the quiver in this case? So you might not immediately recognize it from the picture, but each of these mutations can be obtained in 3 steps. So let's see what happens at vertex 2. Well, first of all, you can see, so I'm only interested in arrows incident to vertex 2. So you can see that there is a directed path from 1 to 5 through 2. And there is a directed path from 3 to 5 through 2. Whenever I see such directed paths, I draw a shortcut. So now you see arrow from 1 to 5 and from 3 to 5. Okay. Then I change direction of all the arrows which are incident to 2. So you can see that these 3 arrows attached to 2 change their direction. But then there is also, yeah.
Mish, I'm a little bit slow. Could you write the monomials corresponding to mutation mu2?
Right. Yes.
That
so
would be useful to look.
Yes. Let me try to do it here. If I all right. All right. So okay. And I'm not as good with the mean. So let me reproduce this picture on another. Yeah. So let me reproduce it here, right? So I have 1, 2, 3, 4, 5, 6, and I think it looked like up to the opposite side, right? Like this. Okay, we'll restore the other arrows in a moment. So this was vertex 2, right? And so there was a variable here that was x2, and this is x1, x3, x4, x5, x6. And so x2 transforms into 1 over x2 times x1, x3, right? So we see that arrows from x1 and x3 are pointing towards x2, plus there is one arrow away from x2 plus x5. All right? So that's a transformation. That's a cluster transformation. Mm-hmm. Okay. But now let me also show you what happens to the quiver. So again, I will just draw parts of it for now. In fact, yeah, well, why not keep them all? I think that's correct. Just a second. Yes, and no, I like this, and like this. Sorry. Right. And so, as I said, first of all, I will draw a shortcut, right? So there is a path from x1 to x5 through x2. So I'll draw a shortcut. There is a path from x3 to x5 through x2. I draw another shortcut. And then I will change direction of all the arrows which were incident to x2. All right, and the rest of the arrows do not change. Okay,
And x2 you replace by x2 prime.
Yes, and yes, so variables, x2 is replaced by x2 prime, and the rest of the variables stays the same. All right, like this. But there is a third step in this rule about quiver mutations. So let me, to illustrate the third step, I will need to do one more mutation. So let's just do it. It's a good exercise. So let's mutate, say, at x4 now, right? So this was mutation mu2, and now I've mutated x4. So mu4. What will it give us? So according to our rules, x4 prime now will be 1 over x4. There is only one thing that points to x4, so that is x5. And there is only one variable to which x4 points, plus x1. So this is a transformation of the variable. But now let's see what will happen to the quiver. So I am now interested in drawing shortcuts that go through x4, right? So let me try to do it on the same picture. So see, there is a path from x5 to x1 through x4. So I will have to draw an arrow in opposite direction. Okay. So this was step number 1, and step number 2 was to change the direction of all the arrows which are incident to x4. So I will just draw this locally. So I'll have this, and then I have this strange situation when there is arrow going between these two vertices in both directions, and the rest of it I don't touch. Okay. So whenever I see such a situation, whenever I have this directed to cycle, the rule is to erase it. And this is step number 3. Okay, so that's, well, it sounds strange, but that's what quiver mutation is. Okay. So is it more clear how this is done?
Yeah. Thank you. There. Yes.
All right. So okay. So let me. Yeah. So this is how this process works. So let me repeat. So first step, important step, and difficult step is to find one nice coordinate system. Once you have it, you can define cluster structure. If you are lucky, and what can happen is after these transformations, it's not obvious at all, but after these transformations, you start with regular functions, you obtain regular functions again. And then you can build, you can continue this process, and this is what cluster structure is.
And sorry, I interrupt you again. So
no, it's okay. Sure.
if you go back to our Poisson brackets,
right,
that means your quiver is 1-to-1 to your matrix omega, right? Because that
my quiver is my quiver is is related, so it's not quite 1-to-1. So if you so let me go back to this equation.
I understand that your quiver tells you how many what is the number, the constant, the integer entry is, and which ij connected. That means the line.
Right, exactly. Yes. Yes.
And then you produce new system of coordinates. So you do transformation, and you rearrange the quiver, so you can recompute the new matrix omega, and that will be how the Poisson bracket will look in the new coordinates.
Exactly. Yes. Yes. Absolutely. Yes.
Okay.
Right.
But what I said wrong? You say that I said wrong, that there is not 1-to-1 between the omega and the quiver.
Right. Yes, and I will explain it in the next picture. So it would be if there are no frozen variables, right? If there is well, if I just have to invert omega, then there is 1-to-1 correspondence. But I will show in an example, if there are frozen variables, then it's not 1-to-1, but we shouldn't despair because quiver is still essentially uniquely determined if you take into consideration the storic action that I mentioned before. Because in addition, remember, I also wanted all my variables to be homogeneous with respect to toric action. So if I combine that with property of log canonicity, then the quiver can be restored unique. So maybe it will become more clear if I return now to our example. So let me just go to this example. Yeah, so this I'll just try to explain this picture. Okay, so yeah, what is this? So what I claim it is a description of both initial cluster coordinates, initial log canonical system of coordinates, and initial quiver for standard Poisson-Lie structure on GL5. Okay, so this looks strange, but let's just review this picture slowly. So first of all, as Sasha mentioned, we should have exactly 25 vertices in our quiver because we're looking for a coordinate system of GL5, right? And dimension is 25. Okay, so so I have this 25 vertices, and now I need to explain what are the functions, what are the coordinates that are attached to these vertices, and secondly, well, I will explain the quiver. Well, quiver is here, so quivers and will determine our transformations. Okay, so here, luckily, we can use this picture in two ways. So just imagine that this picture is superimposed on just a 5 by 5 matrix, right? So we have rows, i's, and column, and rows indexed by I and columns indexed by J, right? So
looking on this picture, I can write immediately all Poisson brackets between all variables, right?
Yes.
Because the error tells me it's a plus or minus, all coefficients are ones, and if no connection, it is 0.
Right, exactly. Yep.
Good.
Right. So all I need to tell you now is what are the functions actually, because as we know in GL5, in natural coordinates, the Poisson bracket is not log canonical. So I'm going to tell you how to read off these functions from the picture. So let's just take, well, let's just take, say, vertex, which is numbered 15 here. So it's numbered 15. The numbering comes from the applet that I'm using, so it has no meaning. But let's look at vertex number 15, which is located in row 2 and column 4. All right. So now think about this as a place in a 5 by 5 matrix, right? So start with this element in this matrix, an element x24, and drop the diagonal from this element until it reaches either the last row or the last column. In this case, it will reach the last column, right? So view this place numbered 15 as an upper left corner of a maximal possible square submatrix, which is dense, which has no gaps in rows and columns, that fits into a matrix, right? Is it clear what I mean? So in case of vertex number 15, I'll get a 2 by 2 submatrix. In case of vertex number 11, I will get 3 by 3 submatrix, and so on, okay? And then take a minor of that submatrix. And that is the coordinate attached to the corresponding vertex. And the statement is that all such minors, all minors defined this way, will form a log canonical system on our GL5 equipped with a standard Poisson-Lie structure. All right, so in particular, in vertex number 21, we just have x55. In vertex number 22, we have a minor formed by rows and columns 4 and 5. In vertex number 11, we have a minor formed by the last 3 rows and columns 2, 3, and 4. And you will notice that on the border, we have all these blue vertices, and those are frozen ones. And they represent the maximal family, the family of minors which just grow along the anti-diagonal from, from upper right corner down to lower left and in the opposite directions. And those we will never touch. They're frozen. And why are they frozen from the Poisson point of view? Because vanishing locus of each of those variables, of each of those minors, is a Poisson submanifold in our GL5. And this is how construction will work in general, if we are lucky enough to find this code. All right. So, yeah, please, I know it's good. So any questions too?
No, principally it's okay.
Yeah, okay. Yeah, and so in the case of GL5, I actually could have obtained the system by considering these diagrams that I considered before, right? So the same family of minors that was monomial in terms of weights that I've drawn before would be a family of minors that we discovered here. But unfortunately, this factorization of the Levinsky doesn't always work, okay? So, I think this is a good point for me to ask how much time I have left.
In general, you have an hour, but if you have something interesting to say, we're patient.
All right, so, okay, so this is just one example of where this construction works, and other examples include Grassmannians and like Mueller spaces and spaces of rational functions and so on. But I may be let me stay within GLN and just ask the following question. Well, okay, we started with fixed group and fixed Poisson bracket, and we produced this cluster structure, right? Nice family of log canonical coordinate systems. But there are other Poisson-Lie brackets on GLN. What can happen then? So here, unfortunately, I will have to stick with slides for now because, because otherwise it will be hard. So, well, this is just picture shows there is a whole truckload of Poisson structures that one can use here, right? So we need some entertainment too. All right. So, okay. So the claim is the following, that we can actually associate different non-isomorphic cluster structure with Poisson brackets which appear within so-called Belavin-Greenfield classification. And so this is what I'll have to explain. So first disclaimer is that in general, even if you take SL2 and pick a simple Poisson-Lie structure, which is defined, say, by the simplest possible triangular R matrix, you may not be able to find a log canonical coordinate system which is given by rational functions in natural coordinates. But in the case of Belavin-Greenfield data, you can, and so let me talk about this a little. So let's just skip some of their terminology and just say that there is a family of Poisson-Lie brackets which is defined explicitly in terms of combinatorial data associated with a root system of corresponding Lie group. And this combinatorial data is described as follows. So what we have is, so let's consider all the simple roots. So let's just stick with GLN. Consider all the simple roots, simple positive roots, and consider two subfamilies of the simple positive roots, which have the same cardinality and which are isometric. So for example, well, if you take a single root of A type and map it into another single root, so this will be a good example. So again, we have two subfamilies of simple roots and isometry between them. All right. So this isometry needs an additional condition of so-called nilpotency, meaning that if I start with a root in the first subset and start applying this map, then eventually I will get out of that subset. So in other words, gamma 1, gamma 2 may intersect, may have a non-empty intersection, but if I follow this map, tau, I will eventually get out of this root system. Okay. And then next notion. So we talked about this with Dima. So what is it called? Greenfield double. So we just copied this terminology from papers of Semenov-Tenchansky, but we can write down now a Poisson bracket, which probably there is a Poisson bracket, so which is going to be Poisson-Lie. So what is R here? So this data that I discussed on the previous slide defines a solution of a classical Young-Baxter equation. And then, given a solution of classical Young-Baxter equation, one writes down this Poisson bracket explicitly, which I am showing on this slide. So what is R? So what is this Poisson bracket? What are the ingredients? So the angle brackets are just the Killing form, and nabla L, nabla R are just right and left gradients of a function on a group. And so we take this R. R is an operator in the Lie algebra. We apply it to this right and left gradients. We consider the pairing, so we'll get this complicated formula, which written in matrix entries is going to be even more complicated looking, right? But this is how Poisson bracket is defined. Now, one of the statements of this series that once you have this, then first of all, you can define this operators R plus, R minus associated with a solution of classical Young-Baxter equation, and applying them to corresponding Lie algebra, you'll get two Lie subalgebras in our original algebra. In our case, it's in GLN. All right, and so then you double this Lie algebra, just consider a direct sum of G with itself, and equip it with invariant non-degenerate bilinear form, which is built from the form on your original algebra. So we had a trace form, for example, in GLN, and then we take trace of the product of the first component and subtract trace of the product of the second two components. And all right, so this leads to two subalgebras in the double, which have the following shape. One is just a diagonal embedding of your original subalgebra, and the other one is obtained by applying this R plus, R minus. Okay, so the claim is that these subalgebras are isotropic in the double, and so double can be decomposed as a direct sum. And so they form what's called a Manin triple. And once you have a Manin triple, so that's essentially a definition of a Manin triple. And once you have a Manin triple, you can define a Poisson-Lie structure on the double of the group, which is given by exactly the same formula, except that operator here is just a projection, difference of projections onto these two subalgebras. So we have this again, this even more complicated Poisson bracket on the double of the group. All right. Okay. So
clarify what is the left and the right gradient.
Right. So you consider you consider
F element is a dual to algebra, right?
No, F is a function. F here is a function on the group, or in this case, function on the double, right? And so you can consider its differential at at a given point, and then consider right and left trivialization of this differential. Or in GLN, it simply becomes usual matrix gradient times the element multiplied from the right or from the left. So, or maybe, yeah, so let me maybe right here. So we have, sorry about this. So if you consider nabla L F at F coupled with psi is d by dt F. Now I'm liable to confuse the order of multiplication, but I hope you will forgive me. X times e to the xi. So that's the definition of the left gradient, and the right gradient is the opposite direction, right? Okay. So going back to the slide. So now our original Poisson-Lie bracket can be identified with a diagonal subgroup, diagonal embedding of the group into the double. All right, so why do I go through that? Because it turns out that to find coordinates, log canonical coordinates on the group, it's more convenient somehow to work with the double. All right, and so so we had this conjecture that if you have an arbitrary simple complex Lie group, then for any Levinsky triple, there exists a regular cluster structure which is compatible with the corresponding Poisson-Lie bracket. So let me unpack this statement. So we have a group. Let's keep it to be GLN. We considered one of these combinatorial data, Levinsky triple. We found there is a there is a corresponding Poisson-Lie bracket. We claim that you can find a log canonical coordinate system made out of regular functions on the group, which is which correspond to this bracket. And we also claim that given such coordinate system, using previously described construction, we can define the cluster structure such that after each mutation, we will stay within regular functions. Right, and so this will be called the cluster structure compatible with this Poisson-Lie bracket. So this was our conjecture, and at this point it is essentially established for GLN, but it's not yet clear how to deal with other type. But no, so let's review our previous discussion in this new light. So our previous discussion dealt with the situation where there was no Levinsky data. No subset of roots was moved into any other subset of roots. So this trivial Levinsky data explicitly corresponds to standard Poisson-Lie structures that we discussed before, and it also corresponds to this Vainshtein Levinsky factorization, as we discussed. All right, but here's another example, which is in some sense maximal Levinsky data. So I just want to show it to illustrate how strange corresponding coordinate systems look like. So it's rather amazing that you can still find them. So G is SLN. We can take subset of all the roots except for the first one, and another subset gamma 2, all the roots except for the last one. And the map between them, which now I denote by gamma, is just a shift. So alpha 2 goes to alpha 1, alpha 3 to alpha 2, and so on. And you can see that this is nilpotent because if I start, for example, with root alpha n minus 1, by applying gamma, eventually I will get to alpha 1, which is not in my first subset. So conditions of the Levinsky are satisfied. All right. And this leads to what's called a Kramer-Gervais-Poisson structure on GLN or SLN, if you wish. And well, the claim is that there exists a cluster structure which you can extend from SLN to GLN and then just to square n by n matrices, which is compatible with this strange Poisson-Lie structure. Okay, just to show you how unusual the statement is, here's an example, this comparison of how this Poisson bracket looks, just compared with a standard one, right? So I just picked at random 3 matrix entries. So, this table shows how the Poisson bracket looks for standard case and for Kramer-Gervais case. So it's quite complicated quadratic structure, but still there is a family of functions that make this Poisson bracket log canonical. And to show this, let me just describe. So this gets a little technical, but so if you allow me, I'll just show an example of construction here. Is that okay? Yeah. So, but on the other hand, it's quite concrete. So this is what we're gonna do. So we're gonna, good news is that functions in the initial cluster are still minors, but they're minors of some more complicated matrices. So let's just take 2 of them. So take just two matrices, just 2 n by n matrices, and from them produce 2 other matrices which are no longer square. So I'll just take square matrix X, throw away the first row, and attach a column of zeros. And then I take a matrix Y, which is squares, throw out the last row, and attach the column of zeros on the other side. And then out of them, I am going to build these block matrices of the following shape. Right, so I have this U of X, Y, this is a huge matrix built of these blocks. All right, and I'm going now to build my functions. So here are the functions. And again, they look complicated, but you don't have to pay too close attention to indices. What we have here are just usual principal minors. This is a family theta. And then we have 2 nested families of minors of this huge matrix U. And if you add them all together, you will see that you'll get this way exactly n square functions. So again, they're quite complicated, but they are minors of these composite matrices. And the claim is that these functions are log canonical, these scary functions are log canonical with respect to the scary brackets that I've shown to you before. All right. And then you can, yeah, so there is some reason we guess them, but I don't think I have time to go through them. And so this is a corresponding quiver obtained using the same technology as before, right? So we found these functions, we computed Poisson brackets, they turned out to be log canonical, we obtained matrix omega, we inverted it, and we obtained the following scary picture. But if you look at it closer, it may not be as scary as it seems from the first glance, because just try to ignore all these dashed arrows. If you ignore all the dashed arrows, you will see exactly the same pictures that we've seen before for the standard case. And so this is amazingly more general statement, and it works in more general situation. But we have much fewer frozen variables. So the new quiver, even though it's populated completely by different functions, is like an old quiver that we saw in standard case with some additional edges between the first and the last row and first and the last column. All right, so that's just one example of this what we call exotic cluster structure on GLN. But to show log canonicity, we had to go to the double, because otherwise it would be impossible to compute. All right, and so yeah, so one then can prove that this cluster structure is regular. So again, look at this quiver. There is a strange, complicated polynomial in X that sit at each vertex, and you can mutate at each vertex, and this involves division. But you will still, so there will be a cancellation, you will get another polynomial, or you'll get another regular function. So it's regular, And to show it's regular, you have to rely again on this classical determinantal identities, but you apply them to this huge composite matrix. And you can, so as a result, and you can show that for any cluster, you can express every matrix entry as a Laurent polynomial in terms of this cluster. All right, so I think it's getting quite technical at this point, and I promised Demos that I'll maybe get to the double, but I do cluster structure on the double, but I didn't quite do it. So I can skip to this point, or I can.
As you like.
All right. So okay. So let me then skip a few things here, and all right. This is not. Right. So yeah. So let's go back to the double. So what about the standard case of GLN? So the standard case of GLN, well, as I explained, there is a nice cluster structure. But what can we say about the Drinfeld double? It's also Poisson-Lie group, but now we need two n-square coordinates, which would be log canonical with respect to the corresponding structure on the double. And the question is whether or not you have a cluster structure there as well. And well, the answer is not quite. Right, so I will explain this quiver in a second, but I want to say the following. So you can find on the double, a standard double in GLN, you can find log canonical coordinate system. So it is hidden in this picture, which I will explain in a second. You can find a log canonical system, but then you start doing cluster mutations, and this nice properties that you start with polynomial function, you stay within polynomial function, is no longer satisfied. It's satisfied almost everywhere except for one particular function. This particular function, which I will define in a second, it lives in this vertex number 1, in this white vertex of the quiver. And what is the remedy? The remedy is that you have to expand the definition of what you consider as a cluster transformation. So remember, cluster transformation was given by the formula all times nu is equal to sum of two monomials. So this becomes too restrictive, and so you have to go to so-called generalized cluster transformations, where all times u is equal to a longer expression, which is a sum of several monomials. But it is quite natural. This was the first geometric example in which such a notion appeared. And so maybe let me just finish by explaining how this strange functions on the double, even in standard case, look like. All right, so you'll see a lot of them. And so they're color coded. So what is a double of GLN? It is given by a pair of square invertible matrices, right? So the yellow vertices correspond just to minors of one of them. Just usual minors, which are defined the same way that we define them for the standard cluster structure. So the blue, so we have matrices X and Y. Yellow vertices all correspond to minors of X, carefully selected. Blue vertices correspond only to minors of Y, carefully selected. And then for the rest of them, we have this really strange definition. So now I'll list all these functions. All right, so we have just dense minors of X attached, well, you know, attached to the last row. We have dense minors of Y attached to the last column. Then we have mixed minors obtained by combining columns of X and Y in some square objects. And then we have really strange set of functions which lives in these gray vertices, which are obtained as following. So you consider a new object, X inverse Y. It's not a random, you know, selection, because map X inverse Y maps from the double into what's called the dual Poisson-Lie group, right? So you take this U equal X inverse Y and then build this complicated determinants again, which are based on columns of powers of this matrix Y, of this matrix U, right? And those are attached to grades. So that just shows that you have to be inventive about how you find this log canonical system. And then there is a generalized exchange relation, which is based on another determinantal identity, which is not of Plücker type. And well, I don't think this is a good time to unpack it. So let me just say that there is a longer determinantal identity which works as a prototype for generalized cluster relations. And maybe I should just stop here because it's, yeah, sorry, because it's getting too technical, and I just realized, well, recalled that in Yaroslavl it's actually quite late and people might be hungry. All right, so I'll stop here. Thank you.
Thank you very much. I have a test question.
Yes.
I know the electric solution for the tetrahedral equation.
Right.
Is it suited for your definition for the generalized cluster transformation?
It's a little different, and I explain how. So generalized cluster transformations that we use here can be obtained as applying, so it can be written as follows. The right-hand side can be written as monomial in many variables times a polynomial, maybe of higher degree, but in a single monomial. And the relations that you refer to is more complicated, right? Because it cannot be written that way. You cannot factor out a single monomial and have a polynomial in one variable. But it fits another formalism, this formalism of Laurent phenomenon algebras by Lam and Polowsky, as you know, it fits it quite well. But Poisson side of that story is not clear at all. So it's a very interesting question to see if there are compatible in some sense Poisson structure in that situation. In general, yeah.
May I ask you? Well, it's not exactly about your talk, but I just thinking. This is, you know, the Poisson structure you describe and all this mutation transformation. It is any quantum counterpart of that? I mean, is any non-commutative algebra and with a similar properties and structures, you know, which resembles, or maybe in some quasi-classical limit or classical limit would go to this Poisson structure that you described to us today?
Right. So yes. So the answer is yes on both sides of the story. So on the cluster side, there were there are two competing notions of quantum cluster algebras. They are closely connected. They're essentially the same up to some normalization. So one is by Vainshtein and Levinsky, and another one by Fock and Goncharov. And the idea behind both of them on the Poisson side is the following. So we had this. So what is a cluster made out of log canonical coordinates? It's a Poisson torus, and Poisson torus is easy to quantize. To quantize naively, right? So instead of
like Weyl algebra, you know, you
exactly, yes,
exactly.
Right, exactly. So you have, so you have instead of Poisson bracket of two things equal constant times their product, you have commutator of two things, or you have, well, variable x times y is equal q to some degree equal times y times x, right? So this Poisson tori I replaced by quantum tori, and so Vainshtein, Levinsky, Fock, and Goncharov defined appropriate adjustment of cluster transformation to this situation, right? And so So there is.
What kind of transformation you can do? In classical sense, you can just make any function, but in non-commutative variables, what can you do?
So you have to select. In quantum case, you can. So non-commutative, fully non-commutative stories is much more complicated. But in quantum case, you can define a normal ordering, right? And then you can write. In that ordering, you can write the formula for cluster transformation, which works, which is consistent with all this story. So
normal ordering, because you can swap all variables using your omega. Yeah.
Right. Exactly. Right. And so of course, as standard example of class Poisson manifold that has cluster structure is say GLN, or simply groups with a standard structure. You can apply this to the quantum version, so to quantized universal enveloping algebras. And again, this has been done by many people in various ways. There is a series of works of Good Earl and Yakimov that deals with so-called Cauchy extensions of nilpotent quantum rings, which has Poisson counterpart. And there is a nice work of Shapiro and Schrader, of Sasha Shapiro and Schrader, that applied this construction based on diagrams that I've shown in the beginning to shows that uses quantum algebra structure to show that quantized universal enveloping algebra can be embedded into a quantum torus, just using these transformations of networks and such. So the short answer to your question, it's a very valid question, and there is a lot of stuff done to it. Right.
And another short question, sorry.
No, it's fine.
Look, you start from some structures like a constant, a canonical, and then Lie algebra, linear, then quadratic.
Right.
Does it make sense to consider non-homogeneous structures? Is it, because it looks like it would be a natural in some problems to have, kind of quadratic and a constant combination.
Right. So in some sense, they do appear. For example, if you consider a unipotent subgroup of GLN, right? Say upper unipotent, a lower unipotent, and you can endow it with a Poisson structure that comes from the Poisson-Lie on GLN, but on this unipotent, on this what's called the fine space, it's no longer homogeneous. It will have a quadratic and linear part.
So that combinations. So just
right.
So it does
constant. Constant I haven't seen, but yeah, maybe you can get that too. But it's reasonable to do that. So and sometimes you can find low canonical coordinates.
Two limits. Two limits, because if you have non-homogeneous, you can consider two limits. One will go to another, kind of
right.
Yes. And all this.
Right. Yes. No. You're right. And there is even work in that, well, in some sense, in that direction by Alexeyev and his collaborator, where they so there is this Ginsburg-Weinstein isomorphism between Lie Poisson and dual Poisson-Lie in a compact group case, and so they consider certain limits that that lead to, in the limit you'll get some cone with low canonical structure on it. So yeah, it's again another good question.
Misha, thank you very much. It was very good and a very good point to start study this subject and work on. I have some other question, but I will write you.
Yeah, sure. Yeah. So yeah, I'll be happy to answer any follow-up questions through any means available to us. All right.
Thank you a lot.
Thank you.
Thank you. Tima, what about the next seminar?
It's under discussion.
Okay, we'll discuss later.
Okay.